All right, what's up everybody? Welcome back. We're going to be doing some more fluid mechanics today. I apologize for my voice. I'm a little sick today, but when you have fluid mechanics to get done, fluid mechanics homework, you got to get it done, you know? So we're off with homework 1, part C. This is the end of homework 1, worthy of celebration, and 4 more problems. So that's what we're going to be working on today. So you can see on the board, we're actually going to be doing our first 2 problems here on the board, and then we'll switch over to the computer to do some coding in Google Colaboratory to solve these first 2 problems through part 3 and part 4. All right, so derive an expression for the force on the end cap of a horizontal cylindrical tank of radius r and liquid level height h. And then we've got part 1 using a Cartesian parametrization, and then part 2 is in polar coordinate systems. So let's go ahead and do that. First of all, what's this problem talking about? Well, we've got kind of like a barrel tank on its side here. Okay, bear with my picture. We've got a barrel tank kind of laying on its side, and it's filled with water. Okay, and do better than that. There we go. It's filled with water at some liquid level height h, and the barrel has a radius r. Okay. And we want to know, we want to derive an expression for the force on the end cap, which is that circular end cap right there. So let's go ahead and just draw that end cap up close. It's going to give us a better diagram since we're dealing with different coordinate systems here. There's our end cap, our water level height. It's arbitrarily right here, it could be anywhere. And once again, this is liquid level height from the ground here, h. If we kind of extend this, the radius is r. Okay, and then part 1, we're going to be using a Cartesian coordinate system. So that's our traditional, xy, 90-degree angle coordinate system. So let's go ahead and establish that right now. We're going to count, well, since we know pressure is dependent on depth in this direction, we're going to count the z direction here. It's positive being downwards like this. Okay, that's going to make it easier for us as we do some math here. Pardon me. Okay. So, how do we go about this? Well, we're looking for the total force again on the end cap. And we know to find the total amount of force something, we have to integrate all of the differential units of force over that area. Okay, so let's go ahead and write that. Well, differential force is equal to pressure times differential area, which we just said. And that's what we're going to be doing for this shape. So we're going to need to find an expression for pressure, and an expression that represents our differential area, and then integrate that along our depth, c. Let's go ahead and start with our expression for pressure here. So pressure, to remember, is rho g z. Okay, and z obviously changes here with depth. So this is going to be easiest if we kind of draw ourselves a triangle. Let's pick an arbitrary depth here. I'm just going to pick right there. And we want to find the pressure there, and we want to stack all those pressures up. And that's how we're going to find these differential units here. Okay, now we know that the radius here is r, and we're at some depth z. Okay, and this is going to represent our differential unit of area right here. Okay, and right now we are looking for pressure. Pressure equals rho g z. Now, to define our axes here, it's going to make it a little bit easier on us. We have to remember that this height below the center of the, so this is the center of the tank, this is the liquid level height, right here. And since z going down is in the positive direction, this distance right here is h minus r. Okay, that's going to be helpful for us. All right, so how do we write an expression for pressure as it relates to the depth here? Well, we can kind of think about this as a linear expression. It is linear after all. Pressure changes linearly as we go down. So we know that at the top of our barrel here, the pressure here is 0. And if we're counting this is the z equals 0 line. Okay, so this is like our axis here, z equals 0. This would be positive z. This would be negative z. Well, we know p equals 0 at a z value of negative h minus r. That's this distance here. And really that's just equal to r minus h, right? Okay, and at the bottom, we have a pressure value equal to rho g z. But z here, remember, is just the radius. So we can write rho g r. And that's obviously at a z value of r. Okay, so if we think about this as a linear trend, I'm going to draw a little graph here where our bottom axis here is the depth z, and then maybe our top axis here is the pressure as a function of depth. Well, we already said at negative h minus r, r minus h, we have a pressure of 0. And then at a depth of r, we have a pressure of rho g r. So let's just call that like right there, rho g r. And it's a linear change. As we go down, pressure increases linearly. And so we can find an expression for pressure based off this line. And we know our linear expressions are in the form of really mx plus b. Well, we're using z in this case, we'll say mz plus b. Okay? So what is the slope of this line? Well, slope, change in y over change in x. Okay? Our change in y values, we said this was rho g r. This was 0. Okay, our change in y value is going to be rho gr. And then our change in x is r minus h. Sweet. Okay, so we can simplify this now. This becomes rho g, let's see, our r's cancel out, and I might have made a mistake here, let's see. Rho g r, let's double check this. We had r minus h, looks right, r, this needs to be this needs to be h, excuse me. Since we're at depth below p equals 0, h. Okay. All right. Now this cancels out, and this cancels out. So we get our slope as rho g. Okay. And then b, our y-intercept is right here. So what does b equal? Well, we can find b by we would take the slope of the line and multiply it by the distance of that, and we get the change here, which is our b, our y-intercept. So let's see, what is the slope? Well, the slope is rho g. And the distance from here to here is, this is 0. It's 0 minus r minus h. Okay. So B equals rho G H minus R. Log right? All right. So we get a final expression then for pressure. This kind of all leads to this, right? Pressure as a function of Z equals our slope, rho G times Z, plus B, rho G times H minus R. We can simplify that, pull out the rho G, Z plus H minus R. Okay, so that takes care of our expression for pressure. Now, what is our expression for the differential unit of area? Obviously, we're going to be looking for this in terms of Z again, since our pressure expression is in terms of Z, and we're also going to be integrating with respect to Z here as we go over the depth of the total object here. So, like I said, with this arbitrary depth here I've chosen, we have a differential unit of area of this, okay? Well, we know that the total, this is going to be like our differential height here, dz, and then this is going to be the length. We need to multiply the length by the differential height to get that differential area. So the length of this whole thing is 2 times the length of this triangle right here. We can just apply Pythagorean's theorem. We know that this length, whatever it is, let's see, it's the square root, let me draw up here, of r squared minus z squared, right? Z squared plus, let's call this x, z squared plus x squared equals r squared. We don't have this one, so r squared minus z squared, square root of both sides. Yep. So dA is equal to, we have 2 of these, is the length. And then we need to multiply it by the differential unit for height, dc. Okay, so that's dA. We can put this this expression together with our expression for pressure now, since they're both in terms of z, and we should be able to get our expression for total pressure, or force, excuse me. So we have force total equals the integral, then we have pressure, which is going to be this right here, rho G Z plus H minus R times dA, which is 2 radical r squared minus z squared dz. All right, and then what are our bounds of integration here? Well, we're integrating from z equals r minus h all the way to r, z equals r. So that's going to be our bounds of integration. We have r minus h all the way to r. I'm actually going to rewrite this as negative h minus r. I know it's a little bit counterintuitive, but that's going to help me remember that we're going from a negative z level to a positive z level, which makes sense in my head better. Okay, so this is our expression now. That integral sucks. So we're not, this answers the first part of question 1. We found the expression. We're not going to solve it until number 3 here, when we can code this into Google Colaboratory. It's going to help us with our numerical integration. It's going to make it a lot easier. This isn't really a fun integral to solve. So we're going to hold this right here as our expression. I'll write that down. Okay, and we should be good to move on to part 2. We're going to do this exact same problem, but with a polar coordinate system. let's go ahead and make some more room. Hello everyone, I apologize for the cut in the video. However, when I was at the whiteboard previously, I solved the problem in a way that would have misled my loyal viewers. I made a crucial mistake about halfway through the problem and didn't notice it and continued on. So I'm refilming this part of the problem. It's the same problem still. We're using a polar coordinate system to solve, or to derive an expression rather, for the total force on the end of that barrel at a certain water depth h. But you're joining me this time from not a whiteboard, but my white wall. It's the best I can do, so bear with me, and we'll get to solving this problem, hopefully, the right way this time. All right, so let's go ahead and redraw our picture. We're using a polar coordinate system this time instead of a Cartesian coordinate system. The only real difference to that, obviously, is we're using radiuses and radians to measure our coordinates rather than x coordinates and y coordinates. So if we have our circular end to our barrel, okay, and again, it has a center point there and some liquid water height. We'll call this height h. Again, it has a radius of r. Okay, and what else do we need? Yes. Once again, if this is our radius r and this is our water height h, then the distance between the centroid and the height of the water is going to be h minus r. Okay, so let's get to solving this problem. Just like before, we're going to need a expression to represent the total force. That's what we're trying to find. And just like before, we're going to integrate pressure times a differential unit of area to get those differential force units accumulated over the entire region here. Okay, so we need to find an expression that represents the pressure throughout this surface, and then a expression that represents the differential unit of area. All in mind, keeping in mind we're using the polar coordinate system. Okay, so let's see, how do we approach this? So let's first find an expression for pressure. That one's going to be pretty straightforward, and just like before in all of our pressure problems, pressure is equal to rho g times some depth in the fluid z, okay? And obviously in this problem, the depth increases as you go below the water height, okay? So rho and g are constant, which is nice for us, but obviously our depth z is going to change as we integrate radially here around our circle. So let's go ahead and find an expression for pressure involving z. We're going to get z in there as a function of theta. All right, so assuming that this is an arbitrary water height h, we can draw this line from the center of the circle up to where the water height is. And we know that at this height, the pressure is 0, at least gauge pressure. It's atmospheric pressure, but relative to the water, it's 0. And with the horizontal, this line makes a angle, we'll call it theta naught, okay? This is going to act as our baseline for what we can compare other pressures to at different depths, okay? So the depth at this point is h minus r, but it's also relative to the central axis here. It's going to be r sine theta naught, right? That's the distance from here to here. That'll be important here in a minute. Now let's take another arbitrary depth, let's say like right here, okay? We can draw another line to that, and we'll say that this is some angle theta away from the horizontal as well, okay? So we want to know now, what is the depth of the fluid here at this angle theta? Well, we can compare it to our baseline theta naught and the depth there, okay? So if the depth here is, again, r sine theta, right? That's this. We can compare it to our original r sine theta naught for the difference in depth, because that's what's going to give us our pressure, okay? So this distance here, call that x really quick, x is going to be the difference between r sine theta naught and r sine theta. Okay, we can simplify this to say r times sine theta naught minus sine theta. All right, and we can add that right back into our expression for pressure, knowing that these two are constants. I guess I should have used z here, right, as our variable. That makes a little bit more sense since we used it here in our expression. Okay, so z equals this. We can add this right back into our pressure expression here, and we get pressure is equal to rho g r times the sine of theta naught minus the sine of theta. Okay, great. Now let's go ahead and look at our expression now for the differential unit of area A. So again, I'm going to pick a arbitrary depth here. Let's just pick one in this quadrant. Doesn't matter. Okay, and this is going to represent our differential unit of area. Even though we are integrating with polar coordinate systems, kind of going around radially, it's important that our differential unit of area uses the different across the differential unit, the pressure needs to maintain constant. So if we were to use sectors rather than strips like this, well, a sector has a different depth at the bottom of the sector and the top of the sector, right? Our infinitely thin area here has no difference in pressure from the bottom and the top, and that's going to be key to solving this problem. All right, so here's our arbitrary depth now. We'll say it has depth z from the center of our circle, and again we know that this is r, okay? And if this represents our dA, our differential unit of area, well then it must be some length times a differential unit of depth, z. That's this right here, okay, z. Great, so what is the length? Well, we can again use some angles here. If this is our angle theta now, and so is this, and the length is r cosine theta. So we get right over here, dA equals r cosine theta times dz. Okay, well this would work out great if we could integrate this with z instead of theta, but remember we're putting this all in terms of theta because we're using a polar coordinate system. So we've got some of the expression in terms of theta, but we can't leave this dz here because we're not integrating with respect to z. We're going to be integrating with respect to theta as we rotate around the center of the circle. So dz is a little bit more tricky to find in terms of theta, but there is a rather intuitive way of doing it. Well, from this expression, or from this diagram here, we know that z is equal to r sine of theta. Right, you can see that here with our relationship with our right triangle. Oh, and you know what? I'm just looking back now, and I made another mistake. Our length here, it's not just r cosine theta, but it's two of those rather. So it's important that we multiply our length factor there by 2. Can't forget that. Okay, back to z, I'm sorry. So z is equal to r sine theta here in this diagram. We can see quite clearly. Now dz, we can take the derivative of that. It's rather hard to find dz graphically, draw it out. It's harder to understand. It's easier to just kind of do the math on this one. Differentiate both sides. We get dz is equal to r cosine theta. We're taking the derivative here with respect to theta. It's important that we do the chain rule times d theta. And now we have dz in terms of theta completely in differential units of theta. Okay, so now we can plug this back in to our dA expression, and we get dA equals 2r cosine theta times r cosine theta d theta, or 2r squared cosine squared of theta d theta. Okay, we now have an expression for differential unit of area and pressure, so we can combine those into our integral to get an expression for the total force on this end wall here. Okay, so we get force total equals the integral of pressure, which is rho g r sine theta naught minus sine theta times our differential unit of area, which is going to be 2r squared cosine squared theta d theta. We can make that expression a little bit simpler here. Rho g r cubed, and 2, always forget that 2, and then sine theta naught minus sine theta times cosine squared theta d theta. Okay, last thing we have to do, make sure we got our limits of integration in here. When we're doing this, we need to integrate around half of our circle. The other half is mirrored. That's what causes the pressure, right? It's just like a tensile force. You can't just call one side the tension, the other side nothing. So we're going to integrate from here up to r theta naught. So this spot at the bottom of the circle would represent, I guess, negative pi over 2. And then we're going to integrate around up to our theta naught. Now, theta naught is a little bit tricky to have in here since our unit here of integration is theta, so it's not really proper. Rather, we should express theta in terms of either radians or some other parameters in the expression. Well, we have height and radius, so we should do that. So theta naught equals what? Theta naught, if we look at it here, I know my drawing is a little bit covered up, I'll redraw it. So if this is our water level, okay, and then we have the horizontal here, this is theta naught. This distance here is h minus r, and this distance is r. Okay, so if the sine of theta naught is equal to h minus r over r, then theta naught equals the arc sine of h minus r over r. Okay, so that's what we should be integrating to. You can go from negative pi over 2 to theta naught equals the arc sine of h minus r over r. And then just fill the rest of this in. R cubed sine theta naught minus, make sure our parentheses are right here, sine theta times the cosine squared of theta d theta. Okay, and this expression should summarize exactly what we need. We have we're looking for force total. Okay, so just like part 1, this expression for force as an integral is very hard to solve directly by hand. So we're going to turn to the computer and use some Python coding in Colaboratory, and we'll solve this with numerical integration on Python. Stick with me for one more jump cut, and we're going to cut over to the computer and solve both part 1 and part 2 with some numbers on the computer. All right, welcome back. We're going to continue chugging along with this problem, part 3 and part 4. Obviously, you're joining me now on the computer. It's easiest to record this through a call like this because we're going to be using Python to accomplish part 3 and part 4 of this problem. So with that, I'll go ahead and share my screen. You won't see this view of me anymore, but you will still see me through this side of the screen, and I'll be working right here on my monitor. All right. Give me just one moment to share my screen. Okay. Looks like we are successful now in sharing that. Great. Alrighty. So picking up right where we left off, part 3. Use Python scipy.integrate.quad to numerically integrate and compare the results from the Cartesian and polar parametrization for a radius of r equals 1 meter and liquid level height of h equals 1.5 meters. And then I've gone ahead and copied, just so we remember, our results from part 1 and 2 here. This was the expression for total force we got from part 1, which we'll put in here first, and then this is the expression for force we got from part 2 using that polar parametrization. So with that, let's go ahead and code in this part 1. So the first thing we're going to do is import numerical Python and scientific Python. That's going to help us greatly. So we're going to import numpy as key, and then we'll import scipy as sp. Okay. And then I think with that we can get started. So the first thing we're going to do is define an integrand, just so we can call it back later when we do decide to integrate. So let's go ahead and define for part 1 our integrand. We'll just call it integrand 1 or something like that. Okay. Define integrand 1, and remember we used the variables here, z, h, and r. When we call this, we want it to return for us the following. So looking at our thing here, we get z plus h, r, and I'm leaving the constants out of it. Well, not the constants, but I guess I'm leaving row g and yeah, we're going to leave a row and g and all of our numerical constants out. Okay, so we get z plus h plus r. I apologize again for the stuffy nose. Here we have the square roots of r squared minus z squared. Okay. All right, so when we call integrand 1 now, we'll return this z plus h. Oh, this should be minus r. Like that. Z plus h minus r times the square root of r squared minus z squared. Great. Okay. And now we can actually do the integration. I guess we can put in our integration we have. So r is 1, h is 1.5. We know that rho is 1 is 10 to the third, and g is equal to 9.81 meters per second squared. Okay. Now do the integration. So we brought our constants out of the integrand, so we have to bring those back in. So we're going to do 2 times
let's see, rho times G. Anything else? I think that's it. Yep, times. Now we can do the integration. So we'll do SciPy dot integrate dot quad. Okay. And we need to put in our function. Well, we're putting in our integrand, so that's easy. We named that one already. 1. And we are integrating from, what were we integrating from? It would have been, is it h minus r to r? Oh, you know what? It was r minus h, because it was negative h minus r. So r minus h, comma r. Then we just need our arguments set as, so we have h and r. And then we're going to want the value without the error. We're good there. Why did it tell me I need this? What is this for? Oh, okay. Let's see what we get. All right. So that's our result for part 1. It's evaluating the integral that we came up with here. Let's go ahead and do the same thing for part 2 and see if we get the same answer. That will be the true test. Okay. So we're going to define a second integrand. Call this one integrand 2. And then theta, comma, theta dot. Remember, because I've already done this before. All right. And when we define this, we want to return, let's see, what do we want to return? Our integral that we just came up with here. So we've got class of parentheses here, sine, can't just write that either, np dot sine of theta naught minus np dot sine theta times, we have cosine squared, right? np dot cosine theta, make sure this is squared. I think that'll be good there. The rest of the constants we'll add back in afterwards. Okay. So we've defined that. We now need to, we can do our integral now. We have our constants defined here, so let's rewrite our integral expression. We have 2 times rho times g times r to the 3rd power times SciPy dot integrate dot quadrature. And we're going to call integrand 2. We're integrating from negative pi over 2 all the way to theta naught, argument equal theta naught. I got a little happy there. Okay, and then we want to call, we want to call our answer, not the error. Okay, and here. Okay, so theta naught isn't defined yet in terms of the given information, so we should go ahead and do that too. Theta naught. So we said, if you remember from last time, theta naught was the arc sine. Oh, I can't just do that. NP arc sine of h minus r, quantity h minus r, divided by r. Now let's see if that works here. Okay, what do we have? All right, after looking at that for like 10 minutes way too long, I realized that right about here, after I defined our integral, I didn't write the word return. This is why I hate coding. Okay, let's go ahead and rerun that. This should hopefully work out for us. Okay, there we go. So we get the same answer here for our total force. We did the first part. So both ways work. We're happy with that. That's all we can ask for. And let's go ahead and move on to part 4. I think we answered everything. Part 3, right? Compare the results. Yep, they are the same. Great. Okay, let's go ahead and move on to part 4. Let's make a plot of the force as a function of liquid level for those characteristics there. 0 to 2 meters, 25 equal space. Okay, so for our plot, we need a y-axis and an x-axis. I guess we can start with our, well, we're going to have forces on our y-axis, and our x-axis is going to be our, what do they have us doing here? Liquid level, right? But we need our h values as one list for the inputs for this graph, and then the outputs we'll get from our function already. So let's go ahead and make our list of h values here. So I'll just call this h values, and that's going to be equal to, we're going to make a matrix linear space here. Okay, and we're going to go from 0 to, it says 2 meters, which is 2 times the radius. And then we want 25 equal spaces. Okay, and then we also need our corresponding forces. That's going to be equal to forces. We already have our forces. Let's use our one from part 1. Okay. So I'm just going to purely copy and paste this, but it'll be our forces for h in h values. Okay. Oh. H values is not defined. Okay, so again, after looking at it for just a minute, I simply redefined what h was in as the lens space itself, and that seems to work okay. So we're going to continue with that. All right, now we can go ahead and make a subplot. So I have imported make subplots from Plotly, and that's what we're going to be using for this plot generation. So sorry I didn't film that, but I imported it just off camera. All right, so we can go ahead and do let's see, it's make underscore subplot. Okay, and then we need to add subplot itself. That's be a scatter plot. Okay, and we want our x values to be. What do we want our x values to be? It's too late for this. What do we have here? We want H values. That's what it's called. Or it's called. H values. We want our Y's to be our forces. Forces. Then this can be the using markers mode. Okay. And then there you go. This is going to look messed up unless I update the layout. So we're going to update this to with 600 height of 400. And let's see. Oh, you know, this is supposed to be in size. H values is not defined still. That is because this is a lowercase v, isn't it? Yes. Okay. Oh, and there we go. Okay, so there's our plot now. Force is a function of liquid level for R equals 1 meter, and liquid levels ranging from 0 to 2 and 25 equally spaced values. Thank you for bearing with me through that. Little bug fixes and cuts to find those fixes, but appreciate it. We'll see you next time. This is the end of homework 1, so we'll see you next time for homework 2, part A. Thanks for watching.